All right, let's dive in. Today, we're going to go behind the screen to get a handle on the very heart of all modern technology, semiconductors. We're going to explore the fundamental physics that literally powers our world, but we're also going to look at it through a really unique lens, one that connects quantum mechanics to a much older concept of order and, well, purpose. So let's get this journey started, not with an equation, but with an idea. So we start with this verse from the Quran. It's all about a universe that's designed with incredible precision, with order, and with a purpose. Now, I know what you might be thinking. It seems like a strange place to start a physics explainer, right? But this very principle, this idea of a measured, determined order, is really the philosophical bedrock for everything we're about to explore. And believe me, that is not just some abstract idea. That principle is literally the reason the device in your hand or sitting on your desk actually works. The controlled flow of electrons making this image possible, that's a direct result of us harnessing the precise, measured properties of matter. So here is our roadmap for today. We're going to kick things off with an ethical framework for technology. Then we'll get right into the nuts and bolts, the physics of electrons and conductivity. After that, we'll see how we can intentionally design materials, we'll explore the whole idea of perfection and imperfection in their structure, and finally, we'll take a huge leap into the super strange world of quantum tech. First up, technology's ethical compass. Because before we even get into how this technology works, the source material really wants us to think about why we build it in the first place and, for what purpose. The core framework we're looking at here is called Maqasid ash-Sharia. Now, the easiest way to think of it is as a set of higher goals meant to guide progress. The point isn't just to innovate for the sake of innovation, but to innovate in a way that actually serves humanity, protecting our well-being, our ability to learn, and the world we all share. And this framework gives us two really key principles to play with. Maslaha, which is all about creating benefit, and mafsada, which is about avoiding harm. And as you can see, it's pretty clear. The exact same semiconductor tech that gives us life-saving medical imaging can also be twisted and used for unethical surveillance. The technology itself, it's neutral. The ethics, the good or the bad, that comes down entirely to our intentions and how we decide to use it. Okay, so with that ethical foundation set, let's dive into the physics. Section 2, the electron's world. This is where we uncover the fundamental rules that make all of this possible. Almost everything in electronics really comes down to this one core concept, the energy band gap. Just imagine it's a hurdle that an electron has to jump over. If it can clear that hurdle, boom, it's free to move around and conduct electricity. The height of that hurdle, the band gap, that determines everything about a material's electrical personality. This table lays it all out perfectly. In metals, the electrons are basically a free-for-all. In insulators, they're on total lockdown. But the magic, the real action, happens right there in the middle with semiconductors, like silicon. Their hurdle is just right, and that means their conductivity isn't fixed. We can actually control it. And that one simple idea, controllable conductivity, is the foundation of every single computer chip ever made. And that brings us perfectly to our third section, designing with impurities. This is where human ingenuity really steps in to tame these materials and unlock their incredible potential. So a pure, or what we call an intrinsic semiconductor, is kind of like a quiet side street with barely any traffic. It's not very good for conducting electricity. So the big question is, how do we turn it into a bustling 6-lane highway? Well, the answer is a process called doping. And honestly, it's a lot like baking. You start with your pure silicon, and then you add just a tiny, precisely measured amount of a special ingredient. That's your dopant. This adds new charge carriers that really get the traffic moving. It can either add extra electrons that are free to roam around, or it can create an electron vacancy, a space where an electron should be. We call this a hole, and it acts just like a positive charge, opening up a whole new lane on our electrical highway. And by picking our dopant carefully, we can create two distinct flavors of silicon. N-type, which is rich in negative electrons, and P-type, which is rich in those positive holes. These two materials, they are the simple, fundamental yes and no, the on and off switches that form the basis of all digital logic. It's that simple. Okay, let's zoom in even closer now. Section 4, order, defects, and structure. This is where we're going to connect the atomic arrangement all the way back to our philosophical theme. In their ideal state, semiconductors are things of just incredible beauty and order. The silicon atoms arrange themselves in this perfect, repeating three-dimensional pattern. It's called a diamond cubic lattice. It's a structure with just immense stability and symmetry. But here's the thing, here's the reality. No crystal out there in the real world is ever truly perfect. There are always going to be flaws. An atom might be missing, which creates a vacancy, an extra one might be squeezed in where it doesn't belong, or you could have a whole line of misplaced atoms. And these aren't mistakes, they're just an inevitable part of nature. And this brings us to another moment for reflection. This verse speaks to the perfection of the Creator's work. So how do we reconcile this? Well, the source suggests the verse isn't really about flawless physical objects, but about the perfection of the Creator. So our job then isn't to try and create some perfect, useless crystal. No, it's to understand the rules of the universe, including its natural flaws, and use them for a purpose. And here's the most beautiful part. Sometimes, like with doping, our greatest achievements come from intentionally introducing a precise imperfection to create something incredibly beneficial. And that leads us right into our final section, the quantum leap forward. This is what happens when we start shrinking our technology so small that the classical rules of physics just start to break down. So, welcome to the wild world of quantum confinement. When you make a piece of semiconductor incredibly tiny, we're talking just a few dozen atoms across, you start to squeeze the electrons. Their space to move becomes so restricted that their energy isn't continuous anymore. It becomes quantized. That means it can only exist in specific, discrete levels. And this completely changes how the material behaves. This whole journey is just fascinating. First, you can squeeze a material in one dimension, which creates a quantum well. In there, electrons can only move on a flat plane. Then, you squeeze it in a second dimension and you get a quantum wire, where electrons can only travel along a single line. And then, if you can find it in all three dimensions, you create a quantum dot. Basically, a tiny prison for electrons, where they're trapped in a single point behaving almost like an artificial atom. And so, that's where we end. From the grand, divine order of the entire cosmos, we've journeyed all the way down to a single electron trapped inside a quantum dot. All this technology, at the end of the day, is a tool. It's a gift we've derived from understanding the precise, determined rules of creation. And that leaves us with a final and pretty crucial question. As we keep unlocking these secrets, how will we choose to act as stewards of this incredible power?